Good morning, everyone. So this is a quick reminder about exam 2. If by now you're not up to date and in parallel that you finished chapter 18, 19, and 20 and you're familiar with the material, uh, you should. You should be up to date with the homework. And I'm just warning you because I don't want you to start falling behind. Uh, Try this week and probably this weekend kind of you need to be up to date with that. So the practice exams, there are 2 different practice exams. Each one will be in 2 different timings, so total of 4. They are on OWL. The study guide for exam 2 is on OWL. The summary of the reactions is on OWL. The chapters included 18, 19, 20. So we already finished all of these last week, all these chapters last week. And the mechanisms you're responsible for, in the sense that I'm going to ask you which of the following is the right mechanism, are these 3. Do you have a question for me?
Yeah, in the practice exam, will we be able to retake it indefinitely, or is it just like a...
The practice?
Yeah, like the last practice exam, the harder one, we could retake over and over, and that was really helpful for me. Will we be able to do that again?
Exactly. So the intensive one, the intensive practice exam, you can take it unlimited. I put it 1 unlimited and 1 hour because, as you said, it helps a lot, like learning the material, especially for the more challenging. As usual, start with the practice exam, then with the challenging. I wouldn't directly jump to the challenging because that can be, if you didn't master the reactions themselves, that can be discouraging and you're going to feel, oh, I don't understand the material. It's going to give you a false evaluation that you don't know the material. While you know, but you need a little bit more work on the reaction to get to the intensive. Any other question about the exam? Okay. So today we're going to start with chapter 22, which is carbonyl alpha substitution. Again, we're talking about carbonyl compounds. So from now till the end of the semester, we're going to keep talking about carbonyl compounds in different contexts. So in here, in this chapter, as the title indicates, that we're going to talk about the alpha carbon substituting the alpha carbon. And mainly what we're going to substitute, if there is a hydrogen, an alpha hydrogen, the hydrogen that is connected to the alpha carbon is called alpha hydrogen. So if there is an alpha hydrogen, we're going to learn how to substitute that and why we can substitute it. So we're going to see in this chapter, all the reactions we're going to discuss are on the alpha carbon. Now, just as a reminder of what we discussed on the chapter before, like in chapter 19, all our discussion was we're adding a nucleophile. The nucleophile is attacking the carbon of the carbonyl. That's a chapter 19. Chapter 22, we're not gonna discuss the carbon of the carbonyl interaction. We're gonna discuss the alpha. Not that the reaction, if I add a nucleophile, it wouldn't attack the carbon of the carbonyl. It will, but our discussion now is on the alpha. So let's start with the first idea in here. So in here are the pKa's of acetone and that of an ethane. And I highlighted the hydrogens that I'm referring to for a pKa. So I'm saying if this acetone loses one of these hydrogens on its methyl, the pKa of that is 19.3, while that of an ethane, the pKa is 60. Clearly, this is much more acidic than the ethane. Clearly, it's not as acidic as carboxylic acid, which we learned the pKa is between 2 to 5. So it's not as acidic as carboxylic acid. Yet if I'm comparing this acetone or the acidity of the alpha hydrogen of the ketone in here and that of an alkane, it's much more acidic. Now the question for you, how would you explain this fact? Why would be the alpha hydrogen in an acetone much more acidic? Remember, the pKa is a logarithmic scale. So that 10 to the power, the Ka is 10 to the power minus 60 to the Ka 10 to the minus 19.3. Big pKa difference. So I'd like you to take 1 minute and think about explain. So anytime we're asked about the acidity, the method that we usually use in organic chemistry, draw the conjugate base. figure out which has a more stable conjugate base. The one with the more stable conjugate base is the more acidic. So I'm going to use exactly the same method to explain the fact that the acetone, the alpha hydrogen of a carbonyl, is more acidic than that of an alkane. So drawing the conjugate base, that means after one of the hydrogen left as H+, that means it left its electron behind. Is this in here compared to this one? So at the first glance, they look equivalent in the sense that the minus on both of them is on a carbon. So I'm not comparing a minus on a carbon compared to an oxygen, and then I can discuss the electronegativity. But one thing about this in here is it has a resonance structure, and it is close to a carbonyl that is kind of withdrawing group, and that's for a carbanion is stabilizing. So two reasons. One, close the minus, the carbanion is close to a carbonyl that is kind of withdraw the electron, and it has a resonance structure, making it, so resonance structure, I'm going to draw the resonance structure so that you can see that. And in that resonance structure, the minus is on an oxygen, which is much better than being on a carbon because oxygen is more electronegative than a carbon. So this resonance stabilizes. This is more stable. And definitely I'm comparing it to this, which doesn't have resonance structure. The charge is localized, which makes this more acidic. Actually, this whole chapter based on the fact that the alpha hydrogens of a carbonyl always going to have a conjugate base that has a resonance structure, and that stabilize it, and that's make it acidic. Now the fact that it is the pKa is 19.3, I need really a very strong base to deprotonate that hydrogen. Like the OH minus, which is the conjugate base of water, and water has a pKa of 14, it's not good enough. I need the conjugate base of an acid that has a pKa more than 19.3 so that its conjugate base is stronger. So OH minus, if I add OH minus, it's going to be an equilibrium reaction going back and forth. And we're going to discuss how that's going to affect the whole deprotonation if I use OH minus or RO minus, one of those alkoxides. Now, usually what we're going to use, I'm just going to go to the next slide and come back. So what I'm going to use usually is a very strong base, and that's going to end me up with the carbanion that we discussed a minute ago. But the aim is not the carbanion itself. This is not the aim of this chapter. The aim of this chapter is once I get the carbanion, so my first step is using a very strong base that we're going to discuss in a minute. The next step is adding to this an alkyl halide, an R'(X), where this gonna attack it. I'm gonna end up with the R'. This is very useful. I'm adding an R'. This R' can be methyl, ethyl. And we're gonna talk about the limitation of that R' in a minute. So the R' is now attached to the alpha. For a ketone, we were only able to add alkyls to the beta if it is an alpha beta unsaturated ketone. This is the first reaction where we're discussing adding alkyls to the alpha. We're gonna see that also we can add halogens to the alpha in the same way. This is where all the discussion gonna happen today. Mainly this is the idea, going from one slide to the other. We're gonna discuss the bases that we're gonna use and how that's gonna affect that substitution, and what are the possibilities of what we're gonna add to the alpha. So let's start with the very basic. Now the base that we're gonna use, as I said, it should be a very strong base. For this one, the pKa of this, which we call LDA. So we use the shortcut of LDA, lithium diisopropyl amide. I'm always not gonna refer to it in the structure because it's a big structure. We refer usually to it as LDA. The pKa of the acid form of it is 36. So this is the conjugate base of an acid that has pKa of 36. So this is a very strong base. Now, the strength of this base, one, because the minus is on a nitrogen, not on an oxygen, so it is stronger. The other thing is about this base. All right, so this, most bases are, strong bases are strong in nucleophile. Is this a strong nucleophile? Would you consider this LDA a strong nucleophile? Who vote for yes, it is a strong nucleophile? No. Don't be shy. Is it a yes or a no? It's a no because it's negative. Actually, nucleophiles are negatively charged. And bases are negatively charged. Now, it isn't a good nucleophile because this CH, I want you to kind of think about it. This is a CH that is connected to a CH3 to a CH3, then a CH to a CH3, and that carbon is connected to the 3 hydrogen. This is a strictly hindered nucleophile. So it is a bulky nucleophile, a bulky base. If it wanted to attack the carbon of the carbonyl, it's gonna fail because of the bulkiness of that. This is why we choose this LDA as our base in this case. One, very strong base, much stronger in pKa than the about 19.3, 16.3 for the ketone. Second, it is a bulky that I don't have to worry about the substituting or a nucleophilic attack on the carbonyl. So the result of this is the deprotonation of the alpha carbon, as long as the alpha carbon has at least 1 alpha hydrogen, which is the case in here. Now, since the molecule is symmetrical, it will not matter whether I deprotonate the left side or the right side of the molecule, or the alpha, the right alpha, or the left alpha. So the next step that's going to happen is, as you know, that this has a resonance structure. And we call this the enolate ion. En or En because it's double bond, olate because we have this O minus in there. So when you're doing the practice and on OWL, it's going to ask you draw the enolate ion of each one of the following compounds. What it means is that deprotonate the alpha and draw the resonance structure. Now this lithium in here is coming from the lithium of the LDA, if we add LDA. So here is the enolate ion of this compound. Usually it happens if I add a very strong base, it goes to the enolate ion. Okay, so let's go. So one thing about ketones and aldehyde that we didn't discuss directly in the chapter 19 is the fact that ketones and aldehydes go from their keto form to their enol forms. Now for ketones, this is an equilibrium reaction, but as you can see percentage-wise, 99.995% is in the keto form. So as you can see that the equilibrium is more toward the ketone than the enol form. And 0.001%. And this is not resonance. This is tautomerization and tautomers. So how do we figure out the enol form of a ketone or aldehyde? So if I'm comparing this ketone to the enol form, mainly what's happening is there is a double bond between the carbon of the carbonyl and its alpha carbon and an OH, and that C double bond O is changed to an OH. The requirement is at least 1 alpha hydrogen. So for this enolation or tautomerization to take place, it needs at least 1 alpha hydrogen. Later on during the lecture today, I'm gonna let you know how did we know that a ketone form, that an enol form will form for ketones. So in other words, if I have acetone in a bottle, this acetone 99% of it is in the acetone form, yet there is a small part of it is in the enol form. Now, definitely, since it's equilibrium, I can push the equilibrium toward the enol form more than the keto form, or the aldehyde more than the enol, based on what I use in my reaction. So, draw the enol forms of the following, each of the following. So what you're gonna do is to figure out the enol or enols form for each one of these. So I'll stop the video and draw the enol forms. I'm gonna open the iClicker for the class. There are no multiple choice, but I want to kind of track you once you finish the drawing. Okay, so we're gonna start with the first one. It is an aldehyde. Is this considered an alpha hydrogen? No. The alpha hydrogen is the hydrogen that is connected to the alpha carbon. So looking at the methyl in here of this aldehyde, yes, it has at least one alpha hydrogen. So we can draw the enol form of this, which is a double bond between the alpha carbon and the carbon of the carbonyl, with that an OH and the hydrogen. And that's the only enol form that's gonna form for this one. Now going to the second aldehyde in here, this is the alpha carbon, no alpha hydrogen. So there will be no enol form. So this aldehyde has no enol form in there. Now going to the ketone in here, it has two alpha carbons, each has at least one alpha hydrogen. So there is a possibility of two enols form. So this is what we're gonna draw in here. So this is the first enol form. And this is the second enol form. So there are cases where we're gonna have two enols forms for a ketone if it has two alpha carbons with each at least one alpha hydrogen. Which is more stable, do you think? I'm gonna call this A and B as a reference. Which is the one that's gonna form more of it, the one that is more stable? A. Why A? More substituted. As usual, most of the times, the more substituted alkene is the one that's gonna be the more stable. So more substituted alkene, more stable. Now, what I tried in this slide to do is to give you different examples, scenarios that you're gonna see for ketones and aldehydes. Two enol form, one enol form, no enol form in there. Now, till now, I didn't tell you how is the molecule, how these tautomers are formed, how it is going from one constitutional isomer to the other. It's going from the keto form to the enol form, just without kind of what are the mechanisms or the steps to go from the keto to the enol form. So let's check first under basic. So this tautomerization, it takes place either under basic or acidic condition. So first I'm gonna start with the basic condition. I'm putting an aldehyde in here, but it will be exactly the same if it was a ketone. So keep in mind that I'm just putting one of them, but it applies for either or. So I'm gonna represent the base as in general. So the base can be OH minus, OR minus, but I'm gonna present it in general B equal a base. So when I add the base, what the base gonna do is it's gonna pick the alpha hydrogen, resulting on the carboanion on the alpha carbon. Definitely now with BH, because the base already picked a hydrogen. I'm gonna keep the same color so that you can see where each is coming from. Now, as we've seen a minute ago and the slides before that, this has a resonance structure. to go to the enolate form. So I'm going to do a double-headed arrow to represent that this is a resonance structure. So we're at the enolate form, but we're discussing how to get to the enol. So the next step is we have BH. Now in here I'm representing it as BH. Sometimes even water, if I have just slight amount of water, would do the trick. So this O minus, gonna pick the hydrogen. And this is how we end up with the enol form in here. So this is how the ketone go to the enol form under basic condition. Now the enol goes back to the aldehyde form in the backward steps. Like the OH, the H will be picked from a base, go to the conjugate, to this one. This has a resonance structure. That resonance structure pick a hydrogen and it goes back to the starting material. So think about all of these as all, oh, sorry, that's not where I wanted that to go. So all of these are, except the resonance structure, all of these are going back and forth, back and forth. Now this is under basic condition. Any questions about any of the steps I did in here? The concept itself? Okay. So now let's do it under acidic condition. I'm going to go exactly with the same molecule, but it also applies if I have, instead of an aldehyde, a ketone. So if I'm starting with an acid, I'm going to represent the acid as HA. So this is the first time we've seen this step I'm going to draw in here, which is the oxygen picking the hydrogen, the C double bond O, the oxygen, is going to pick the hydrogen from the acid. And that would result on this, with this in here. And definitely plus A minus because this is leaving. Now, as you all know that an oxygen with a plus charge, that's not that stable. So that this has a resonance structure where the electron gonna rearrange. So it's resonance, so I'm putting a double-headed arrow. So what I'm gonna do, I'm just gonna redraw this with the hydrogen drawn out just because it's easier to see the next step. So this is exactly the one above it, but this is in with a hydrogen drawn out. So as we've seen in step 1, A minus is produced, which is the conjugate base. So now the A minus, gonna pick one of the alpha hydrogens. The alpha hydrogen will give its electrons. And this is how the enol form is formed. Again, all these steps are equilibrium. So it goes back and forth. So this is exactly this one in here. Those two are the same. So in basic, the OH minus took the alpha hydrogen, then it goes to the resonance structure, then it picks a hydrogen. And here, because we're starting with an acid, the acid protonates the oxygen, the C double bond O. Then after that, the A minus will pick the alpha. So these are the enolation or the tautomerization using acidic or basic conditions. Okay. So we've seen this in chapter 19, and not the mechanism, but the process. And at that stage, I asked you that in chapter 22, I'm going to explain it. Let me just go back to that. So when we did the alpha beta unsaturated ketone, and the nucleophile attacked the beta carbon, we ended up with the, because this has this side and it went to C plus, double bond CO minus, and then the nucleophile attacked, and I told you at that stage that if I have this in here, it will go, I said steps in here, 4 steps, and it's gonna go back to the keto form. The 4 steps is what we learned today in reverse. So this is when we went from the enol form to the keto form. I told you at that stage, just keep in mind that that enol form gonna go to the keto form when we did the alpha beta unsaturated ketone. These 4 steps is the reverse of what we've done today, whether under acidic or basic conditions. Okay, so this is the acidic and basic. This is exactly what I've done in the slide before, but I felt that sometimes it's very helpful for you guys to have them side by side, just to see the difference. If this is kind of confuse you, something like this confuse you, just ignore this slide because we already done it in that 2 slides before. Okay, here we're gonna start with the chapter. We learned how to deprotonate the alpha carbon. Now what we're gonna do after the deprotonation? So first LDA, let me go one more time over this. So we're starting with this in here, and we're adding COCH3. The first step is LDA THF minus 78 Celsius. The THF is the tetrahydrofuran, which is an ether, cyclic ether, and it is inert in the sense that, as we learned in the ether chapter, they don't react with much. So what's going to happen in the first step is the deprotonation, as we learned, of the alpha carbon as long as it has 1 alpha hydrogen. The second step is the addition of this alkyl halide. So this will attack the alkyl and the X will leave. Now the conditions for the R prime X, I think you know them. It shouldn't be, so it can be phenyl, it can be vinyl, it cannot be tertiary, and even secondary it give a poor yield. So in other words, the R prime X, not tertiary and not secondary in this case. The secondary it will go, but it will give poor, this is poor yield. Not phenyl, not vinyl, but allyl and benzylic are the fastest, then a methyl with an X, then an RCH2, then a primary. So all what we have to pay attention to in here, that the R prime is not phenyl, not vinyl, not phenyl, not vinyl, not tertiary, and secondary 50-50 yield. Now, what are the best then? That limits the R prime X to primary, allylic, benzylic, and that's it, and the methyl X. Any question about this in here? All right, so let's see some examples. All right, so I would like you to take 1 minute and draw the product of this of these 2 steps. Okay, so I'm gonna start with the first step, which is LDA THF as a solvent, and the condition is minus 78 Celsius. So the question is, do we have an alpha carbon that has at least 1 alpha hydrogen? So these are the 2 alphas. I'm going to draw out the hydrogens there. So yes, we have, the molecule has 2 alpha carbons, each with at least 1 alpha hydrogen. The question is, should I deprotonate the left one, the left alpha, or the right alpha? It doesn't really matter because the molecule is symmetrical. So either or would end up with exactly the same result. The step after that is adding the iodomethane. So we know that the alkyl halide has a lot of limitations in here. Not tertiary, not phenyl, not vinyl. And looking at this, it's iodomethane, so there is no problem in that. And the reaction itself, or the mechanism, is SN2 mechanism. So we're ending up with the methyl on the alpha carbon. That is powerful. We're adding R groups to the alpha. In all chapter 19, we didn't have any reaction in which I can add methyls to the alpha. We learned to the beta, if I start with an alpha beta unsaturated ketone, I can add to the beta, but not to the alpha. And this is powerful in here, that we can add kind of groups to the alpha. And we're gonna see that in the multi-steps. Okay, now let's take this example. I'm gonna write it this way. What if I have this in here and I added LDA THF minus 78 Celsius followed by iodomethane? I'd like you to figure out the end material of these two steps. So stop the video and try to do it yourself. And the most important thing, to think about why you're doing what you're doing. And for those who are in class, I open the iClicker. Okay, so we're starting with this one. So it has, again, the same equation. 2 alpha carbons. Each has at least 1 alpha hydrogen. But the difference between this and the slide, or the molecule from the slide before, that the molecule is not symmetrical. And I'm going to label this as A, B, C. So the deprotonation of carbon C, which is an alpha, going to give me a different material or compound than deprotonating carbon A. Here is the question, which one should I deprotonate? This is the whole idea in here. So if I add LDA THF minus 78 Celsius, would I end up with a deprotonation on carbon C or on carbon A, and why? Right, let's check. I'm gonna draw both. So if I deprotonate the alpha on C, I'm gonna end up with this in here. This is the, so deprotonation of carbon C, deprotonation of carbon A, both has a resonance structure. So if we look at both of them, both scenarios, this one gives the more stable carbanion that has an enolate form, which is more stable because it's more substituted. Compared to this one, it's less stable than the other one. But looking at what I'm using in this case, which is LDA, is LDA a small or bulky base? Bulky base. From the perspective of LDA being a bulky base, is it easier for it to pick the hydrogen from C or A? A. So this A is less strictly hindered. Yet, if I deprotonate A, I'll get the less stable carboenolate form. We have two things in here. I hope that reminds you with chapter 14, where we had two things controlling the situation. One, the one that forms faster, easier. The other one, which is the kinetic, when we talked about chapter 14, 1, 2, and 1, 4. And the other one is the thermodynamic that goes through the most stable situation. So using LDA, because it's bulky, it's gonna choose the alpha. If the alpha carbons are not symmetrical, it's gonna choose the one that is less strictly hindered, which is in this case carbon A, which results in this carboanion, followed by the iodomethane, which is, I'm gonna draw it in red, and we're gonna end up with the new methyl on carbon A. We call this the kinetic product, the one that forms faster when I use LDA. Go ahead.
So if we were doing that at a higher temperature, would it, or so because it's a lower temperature, is that why it's the less directly hindered?
Very good question. She's asking, okay, 1 minute, when we discussed the 1214, temperature played a big role. Because at high temperature, the reaction became reversible in the 1214. And here, if I increase the temperature with the -78, it wouldn't change it to reversible. What changed the reaction into a reversible one, which you're getting to, which is what we're gonna discuss next, is having a base that is not bulky, that is not that strong. It is strong, but not as strong as the LDA. So if I start with exactly the same molecule, but instead of the LDA, I added OH minus or RO minus, the reaction becomes equilibrium. That equilibriums help us in the thermodynamic, so that will make the most stable carboanion or enolate forms. Then if I add the iodomethane to that, it will end up substituting or adding the methyl to the more substituted alpha carbon. And that's very important. Why? Because you have the control whether you favor the thermodynamic or the kinetic. If you want the kinetic, if we have a ketone that is unsymmetrical, the two alpha carbons are not symmetrical to each other. If you use LDA, it's gonna substitute the less strictly hindered alpha carbon, which is the kinetic, the one that forms faster, the one that is irreversible as a first step. Now, if I want to favor the thermo, which is adding the alkyl, the R prime, to the more substituted, what I can do is use OH minus or RO minus. The fact that I'm using OH minus or RO minus is going to make the reaction reversible, which end up that it goes to the enolate form, then goes back, and then comes back until it achieves the one that is more substituted, more stable as an enolate form. It's almost exactly the same idea of kinetic versus thermo we discussed in the chapter 14, but here not the temperatures that are playing the role, the reagent that I'm using. Does this make sense to you? All right, let me go back and summarize it on that slide so that it is easier for you to study that. So, the treatment with NaOH or OR minus, so I'm going to put in here, if I put first step NaOH or RO minus followed by the iodomethane, I'm going to end up with the substitution on the most, so this is the most substituted alpha carbon. Definitely the alpha carbon should have at least one alpha hydrogen. If it doesn't have at least one alpha hydrogen, this whole discussion is not needed. And this will be the thermo product. Now, if I add LDA THF minus 78 Celsius followed by iodomethane, the new methyl or the R gonna go to the less strictly hindered, and this will be the kinetic. And I already typed down what I'm saying so that you have it written for you if you're doing a review for the exam. So you can either favor the kinetic or the thermal. Questions about what I've done in here? Okay. Okay, so in this molecule in here, we're starting with a ketone, cyclic one, and we add a diluted HCl. Now, looking at this molecule, it has 2 alpha hydrogens, 2 alpha carbons. Does this alpha carbon has alpha hydrogens? This one, let's call this A, B, C. We're talking about carbon C. No. What about, so no alpha hydrogens. What about carbon A, which is an alpha carbon? Does it have at least, okay. So at least 1 alpha hydrogen. Indeed, it has only 1. Now, so how many enol forms are we expecting? Are we expecting for this one, for this molecule, for this ketone? 1, 2, 0, 1. Because we have only one alpha carbon with an alpha hydrogen. Now, what's special about this carbon in here? I hope you can see it, that it is a chiral alpha carbon. Can you see that? That it is chiral because it has 4 different R groups around it? Right. So, we've done this experiment in a lab that we start with this molecule. We add HCl, diluted HCl. Let's say we started with 100% R for carbon A. Then we do this, we put HCl aqueous diluted and we leave it for a little while. We come back and we find that the 100% R of the ketone form ended up with 50 R, 50 S for carbon A. How would you explain that? We call this racemization because we started with a pure R for carbon A. After a little while of the experiment, we ended up with a 50R, 50S, which we call racemization, going from pure to racemic mixture. How would you explain this fact? If you're given that fact, how would you explain it based on, as we just discussed, that this will have an enol form? Because any keto form has an enol form. Yes, it is more, the equilibrium is more toward that. Yes, go ahead.
Because it's planar, it has an equal chance of attacking from the back to the front.
Very good. So she's saying when it goes from the keto form to the enol form, in the keto form, A is tetrahedral. It has the stereochemistry R. Once it goes through the 4 steps we discussed, which is the H+, then the carbocations, and the double bond, this double bond in here, if we're going to go back to the VSEPR and see the structure in a 3D model, that structure is trigonal planar. So now the molecule is a trigonal planar in this molecule, this double bond, this methyl, and this and this one are all trigonal planar. In other words, if we're going to go the steps, as I said, we go to the enol form, but also it goes backward from the enol form to the keto form. When it goes backward from the enol form to the keto form, the H+, it has equal opportunities, since this is a trigonal planar, either to attack from the upper side or the lower side. One of them gonna be R, the other gonna be S. And this is why we end up with a racemic mixture. So in other words, this is how we learned that ketones form. This is the experiment that from which we learned that ketones forms have enol form. Because we started with an alpha carbon that is chiral, and there should be nothing happening. Then after adding HCl to go to the enol form, we ended up with a racemic mixture. And that was the proof that this molecule, this ketone, is not like stay ketone. It's undergoing that enol form and going backward. So To summarize this, when do you think a ketone will have racemization or an aldehyde will have racemization? What are the conditions? Will any ketone have racemization? Any aldehyde out there gonna have racemization? What are the conditions? Go ahead. Very good. Chiral, alpha, carbon. I'm gonna add one condition which is important, with at least one hydrogen, right? Because if it doesn't have a hydrogen, it's not gonna have an enol form. Chiral alpha carbon with one alpha hydrogen. And I say one alpha hydrogen because if it has two alpha hydrogen, it's not chiral. For it to be chiral, it needs 4 different groups. So from now on, when I ask you which of the following gonna undergo racemization, it should be clear for you. For racemization to take place, you need an alpha carbon that has one alpha hydrogen and the alpha carbon is chiral. Does this make sense? Now, if it doesn't have the chiral center on the alpha, it will have an enol form, but it wouldn't undergo racemization. These are 2 different things that we're discussing. It might have an enol form, but it will not undergo racemization. Okay. So let's do an example. And here I just typed exactly what are the conditions for racemization, so that when you're studying. So select the compounds that will undergo racemization in aqueous acidic conditions. Okay. So the most popular answer is D. D, very good, is the right answer. So starting with the first one, this is an alpha, this is an alpha carbon. This one has no alpha hydrogen. So I'm not expecting any enol form from this side. This has 1 hydrogen, yet looking at it, I have to check whether it is chiral or not. This is 1 group, 2 groups, but in here it's symmetrical. So this group in here and this are the same. So it's not chiral. There will be enol form, but it's not chiral. So we have alpha hydrogen, but not chiral. So I'm not expecting racemization for that one. Let's go to B. This is alpha, alpha, both of them 2 hydrogens. So they aren't chiral because they don't have 4 different groups. Yes, there will be enol form, but it wouldn't undergo racemization. This is alpha and alpha, each 2 hydrogens. So clearly they don't, the alpha carbons don't have, they aren't chiral. So yes, there will be enol form, but no racemization. So the reason that I put all of these together, that they are all no, 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 to remind you that for it to undergo racemization, the alpha carbon has to be chiral, has to have at least 1 alpha hydrogen. Now, I've seen for B, I've seen a student in the exams choosing B, or something similar to B, where they think, oh, as long as there is a chiral center on the molecule. No, it has to be the alpha carbon. Or, oh, the alpha carbon in here, oh, this is chiral, although it doesn't have an alpha, they would think racemization will take place. So, with this, we're done from the idea of racemization. Now, we discussed in here in the slides before how to add alkyls to the alpha carbon. But also, we can add halogens to the alpha carbons. And for example, if I add Br2 or Cl2 or I2, any of these, with acetic acid or H+, in here we're using acetic acid, but if we use H+, it's exactly the same. What we're gonna end up with is the bromination, monobromination of the alpha carbon. We're adding 1 bromine to the alpha carbon. Definitely the alpha carbon, for it to undergo this reaction, it must have at least 1 alpha hydrogen. So if there isn't an alpha hydrogen, the reaction will not take place. Now this reaction is a very important reaction. Let me show you why. I'm gonna give you an example that you've seen, like you can relate to from chapter 19. Let's say this is my ketone, and I wanna end up with an alpha beta unsaturated ketone. In chapter 19, we started with alpha beta unsaturated ketone, but I never told you how we can prepare this alpha beta unsaturated ketone. So if I have a ketone in here, which is the cyclohexanone, and I add Br2 acetic acid to it, I can end up with the Br on the alpha carbon. And in here, it doesn't matter whether the left or the right, because as, again, the same reason, the molecule is symmetrical or the alphas are symmetrical. Now, the next step to prepare this alpha beta unsaturated ketone is the elimination of H and a Br, or the Br and an H from a neighboring carbon. This is the Br, here is the H. So I can do that either by tertiary butoxide or ethoxide or OH minus. The end result of that is an alpha beta unsaturated ketone. This is how we prepare the alpha beta unsaturated ketones. It's using the alpha bromination of ketones or aldehydes to get there. And this is why the importance of that Br in there. Actually, that Br can be substituted by a nucleophile. So it kind of opens the door for that too. Now, this bromination or alpha bromination can take place the same as enol, going to the enol form. It takes place under acidic or basic condition. Also, this takes place either under acidic or basic condition. Now, the problem with the basic condition, so the acidic, we add one bromine and everything goes okay. With the basic conditions, OH minus with Br2, it goes out of control a little bit. And what I mean by that, that there might be the formation of one bromination or two Brs, dibromination, tribromination. So it goes out of control. I can't have one end compound. And because we don't know what we're getting, we prefer the acidic method over the basic method. But as you know by now that organic chemists, we like to use kind of reactions like that. If the reaction is not useful to form a one compound, we can do something about it. And on the next slide, we're gonna discuss how we're gonna use this reaction that goes out of control and give a couple of different compounds. So since this reaction, if I add Br2OH minus, I'm gonna have two different compounds. What we do is we use this reaction as a qualitative test. Actually, let me first talk about the reaction, then we go talk about the test itself. So this reaction, as I'm gonna draw it, applies only for methyl ketones. And the methyl ketone is a methyl that is connected, so a C double bond O, and from the other side, a methyl. It couldn't be ethyl, it couldn't be anything else. A methyl ketone is a methyl with a C double bond O from one side and another R from the other side. So we learned on the slide before, if I add just Br2OH minus, it's gonna go out of control. So what we're gonna do is we're gonna add excess Br2OH minus. So we're gonna overwhelm the reaction until it replaces all the three hydrogens on the methyl with Brs. So because I added excess, I can take it all the way toward all those hydrogens, alpha hydrogens are replaced by Brs. If I just Br2OH minus, I'm gonna get couple of different compounds. Excess, I'll change all the H's to Br, substitute all of the alpha hydrogens with a Br. Now the fact that I'm using OH minus, the OH minus gonna attack the carbon of the carbonyl Now, usually when a nucleophile attack a ketone, the next step is this O minus picking an H, right? This is what we've seen in chapter 19. But this is a special compound. And I'd like to have the attention of everyone in the class of what I'm gonna do next, because it's slightly different than usual. Usually this doesn't happen that the lone pairs of the oxygen comes back in a ketone or a tetrahedral intermediate. But in this case, it's gonna come back and kick out this in here. So we're going to end up with this plus CBr3 with a minus. So that carbon left as a carboanion. Then this carboanion, being a minus, is going to pick the hydrogen from this one. The result is this, the conjugate base of that, plus CHBr3. So the result, I'm starting with the methyl ketone, I'm ending up with the conjugate base of this. So as if this carbon is oxidized to the carboxylic acid, then O minus, and CHBr3. Now, let's visit the steps. How in here, why would this leave? Why wouldn't the O minus pick an H? How is it possible that suddenly a carboanion is a good leaving group? Because a minus on a carbon is not a good leaving group. Why in here it is a good leaving group? Let's examine this. Go ahead. No, go ahead.
Is it because the resonance between the oxygen?
You mean on this side?
Yeah.
That's part of it. But before that's formed, why would this even leave? Because it's usually a carboanion is not a good leaving group. But the fact that we have 3 BRs and the 3 BRs are a halogen, which is the most electronegative atoms, or one of the most, that group is the electronegative, that stabilize the carboanion and make it okay for that carboanion to form. Now this reaction by itself, taking, if we start with the methyl ketone, end up with a conjugate with the benzoic acid, the conjugate base of that, it's not a wow reaction, right? Because if I want the conjugate base of benzoic acid, I'll start with benzoic acid and add OH minus, right? That's much easier than this reaction. The reason that we use this reaction is qualitatively. This in here, the 3-bromine, the tribromomethane, is yellow in color. So we use this as a qualitative test to test whether our ketone is a methyl ketone or not. Because this reaction only takes place if it is a methyl ketone. So you're going to do this in the lab, or if you are already in the lab, most probably next week you're going to do it, which is your test. It's part of a test that you're going to do, or the practical in the lab. You're going to be given different ketones and aldehydes, and you're going to do a couple of tests. One of them is the haloform test, which is adding, in the lab, you're going to add iodine instead of the bromine, plus acetic acid. If you have the unknown and you add that iodine and the acetone with acetone, and you see a precipitate, that tells you, that narrow it down that the ketone you're dealing with is a methyl ketone or a methyl aldehyde. Okay? So this is the test. This is the importance of this. We call it haloform or iodoform in your lab, iodoform test. Does this make sense to you guys? So always in an iodoform test, we have to start with the methyl ketone for the reaction to take place, for the precipitate to form. If it isn't a methyl ketone, any other ketone, it's not going to form that. Or any other aldehyde other than a methyl aldehyde, it wouldn't form it. Make sense? So for this to form a precipitate, it needs to be a methyl ketone or a methyl aldehyde. Following can undergo a haloformation. It could be more than one right answer. So it could be 1, 2, or 1, 2, 3, or 3 and 2. So stop the video and do that yourself. Most popular answers are 1 and 3, and 1 and 3 are the right answers. So which of the following undergo haloformation? It has to be a methyl ketone. This is a methyl ketone. So yes, actually it will end up, just let's write the result of that. If it's the oxidation of this to the conjugate base and this CHI3. In here, I'm going to put it X3 because it says haloformation. So yes for that. This, yes, it has a methyl, but this is a methyl ether. The reaction will not take place with a methyl ether. It's very specific for a methyl ketone. In here, it's also a methyl ketone. So the result of this will be this side that I'm circling in green will go to this conjugate. It's going to be oxidized to the conjugate base plus CH(X3). So in other words, if I have an unknown of these two and I add the haloform reagents, it's going to form a precipitate for both of them. So any questions about that? And let me go backward. So this is the end of this lecture.